We travel into space to make discoveries and look beyond reality itself. What if the cosmos is invisible in all its glory? Could it be that our universe is an illusion, a complex facade covered by the complex laws of physics? Our quest leads us into a labyrinth of time, moving endlessly through the universe. Time stretches, compresses, and binds all aspects of existence. It acts as an invisible link, connecting the past, the present, and the uncertain future, forming the foundation of our reality. As our journey reaches its climax, we will encounter two formidable pillars of understanding: the speed of light and the mysterious force of gravity. The speed of light, the boundary that separates the possible from the impossible, and gravity, the invisible force that represents the interaction between all matter, bending the fabric of space and time. Through them, we will try to decipher the cosmic code that governs the universe. Fasten your seatbelts for an unknown space journey, where we challenge our understanding of the universe based on the principles of time, light, and gravity. Everything around us, even ourselves, is part of our universe. We are used to thinking of it as something ephemeral, but what is the universe? Today, we're going to challenge what you know about the universe. What if everything we see and feel is an illusion? Hold on, because we're about to delve into the mysteries of the universe. First, let's look at what we know about the universe. For scientists, the paradox of how our universe was formed is still a mystery. As we know, 13.8 billion years ago, according to the Big Bang theory, the universe was formed from a singularity where all the fundamental forces converged. On the other hand, according to the Hawking-Hartle theory, the universe did not originate from a single point. It existed as pure space without time, with the Big Bang coming later. Despite the diversity of current ideas about the origin of the universe, cosmic inflation began at some point. Protons and neutrons formed in microseconds, forming basic building blocks like hydrogen and helium. Then, after cooling, 360,000 years later, light, and millions of years later, stars and galaxies. As a result of the expansion caused by the Big Bang, we can see other galaxies moving at high speeds. And so, 1 billion years after the Big Bang, the universe as we see it came into existence. But what do we mean when we talk about the observable universe? The part of the universe that we can see may not be very large. It's actually about 93 billion light-years. What each of us sees is the matter and energy that fills space. Surprisingly, the fraction of ordinary matter that makes up stars and planets is tiny compared to the hypothetical dark matter we have yet to detect. However, the most interesting thing we know about the universe is life. According to the principles of physicist Brandon Carter, we exist as observers, and the universe conforms to our existence. And the universe must be like observers. That is, the universe can be such that our existence is possible. This leads to the fundamental question: does the universe exist apart from us? Let's turn to quantum theory. Physicist John Wheeler, colleague of Albert Einstein, modern observations suggest that they can influence the behavior of photons. A famous experiment with photons directed at two pieces and a screen shows that observers with detectors can influence the behavior of photons. Thus, if there are observers, the photons act like particles and pass through one of the two slits. However, without observers, the photons behave like waves and pass through two slits at once. Wheeler decided to take the experiment to the cosmic plane, pointing the photon gun at the quasar and moving the slits to two nearby galaxies. Thus, the photon may have started billions of years ago, before life and the development of photon detectors, forced to go to those detectors. That is, the motion of light always depends on the observer. Does this mean that the universe cannot exist without humans? Not really. It is true that humans are capable of receiving information, analyzing it, and reproducing it for others. But they are not the only watchers, even if they are perfect. Following Willer's model, high-energy particles, which can exist in different states, can interact with rocks on Earth. Thus, the stones will leave a trail of particles, which means that new information has been exchanged. Therefore, according to this hypothesis, the universe does not need consciousness. Another experiment in quantum mechanics confirms this. 3 scientists who recently shared the Nobel Prize, John Clauser, Alain Aspect, and Anton Zeilinger, were able to prove that the universe is not local. This, of course, does not mean that the universe as we know it does not exist. Physics distinguishes between the principles of reality and locality. Reality means that an object exists and does not change its properties even if no one observes it. A red apple will remain with or without measurements. Area, in turn, is explained by the fact that objects can be affected only when they are related to each other. And these distant bodies cannot interact with each other, for example, at the speed of light. If you send a light signal to a friend 10 light years away, you won't get a response after turning on the flashlight. This leads to the principle of local realism or the principle of hidden variables, according to which objects with certain characteristics exist at some intangible level and are independent of observations. In other words, we live in an objective reality with a certain set of factors, independent of our consciousness. But physicist John Stuart Bell disagreed. In 1935, Albert Einstein, Boris Podolsky, and Nathan Rosen published a paper under the acronym EPR, in which the theorists attempted to prove the absurdity of quantum physics. They questioned the possibility of quantum communication. If 2 particles are bound, they are conserved even if they are in different parts of the universe. For example, if a particle rotates clockwise, other particles associated with it rotate counterclockwise. So, if one piece is on Earth and the other piece is 1,000 light-years away, then, knowing the direction or rotation of one of them, one can immediately know in which direction the other is rotating. This contradicts GR because nothing can travel faster than light. So, 30 years after EPR was published, Bell conducted a thought experiment. He continued with the EPR idea, but refined it a bit. He envisioned 2 observers, Alice and Bob, in different parts of the solar system and with particle detectors, but with 2 different settings, A, B, B, for more precise observations. Thus, if the local theory of reality were true, one particle would have no way of knowing what parameters another has. Results are always random. If quantum theory is correct, then the particles would be perfectly correlated. 3 Nobel laureates, Clauser, Aspect, and Zeilinger, were able to replicate the experiment in reality. By counting the number of times Bob and Alice agreed with each other about the state of the particles, they confirmed Bell's theorem, proving that the universe is not locally real, meaning that everything in the universe needs an observer. That's why we can breathe. The universe exists as we think it does. However, what if I told you that this might not be the case and that our brains are deceiving us? From our perspective, according to Einstein's GR, the universe is a continuum of space-time with 3 dimensions and 1 temporal dimension. All massive objects in our universe, including our Earth, can cause gravity to dissipate time. Yes, we monitor all of this. What could be cheating? Perhaps our 4-dimensional universe is a holographic projection. It sounds fantastic, but this theory is being seriously considered by scientists. Everyone has probably seen a hologram, a deep 3-dimensional image created on a flat surface using light. The light produced by the holograms contains a large amount of encoded information. For example, texture or relative distance. Thus, From all angles, the image will appear three-dimensional. Theoretical physicist Juan Maldacena suggests that our universe might be like this. Everything you see in 3 dimensions is in 2 dimensions. Black holes helped develop this idea. Black holes can increase their mass at the expense of other objects falling onto them. But these objects do not disappear. They remain in the black hole. But black holes can decay. Renowned physicist Stephen Hawking discovered that black holes evaporate and then disappear completely. What happens to data that falls into a black hole? Will it be gone forever? This goes against the basic laws of physics because matter cannot disappear. They change to another state according to the principle of conservation of mass. However, the idea of the holographic nature of the universe can solve this paradox. The holographic theory is explained through the hypothetical doubling of 2 other mathematically equivalent theories, the Ads-CFT correspondence. Anti-de Sitter space, ADS, a space closely related to negative space and constant theory, has a curved parabolic shape in more dimensions than required by line theory. This space is often defined as 5 dimensions, but it can have up to 10 dimensions. ADS also has limitations, unlike the popular model of the universe. Modern cosmology suggests a flat universe model, similar to a simple universe, where 2 lines or 2 light waves will always be parallel. If the universe is truly perfect, it may not have boundaries. But it's possible that our universe is so warped in unimaginable disintegration that satellites can't see it. Therefore, the UDS can be thought of as a 3-dimensional ball with a finite surface, but it is very flat. This theoretical limit is crucial for the second theory in this theory, conformal field theory. CFT describes the behavior of particles and fields in flat space and is one-dimensional compared to ADS and has no particular gravity. So there is a dualism that allows us to look at the system from 2 sides. Internally, what is in ADS can be translated to CFT and vice versa. So their duality is like a borderline hologram, encoding everything inside. Thus, according to Ads-CFT, information entering a black hole does not disappear without a trace. Information can be encoded in the 2-dimensional event horizon of a black hole, beyond which the gravitational disturbance is so strong that even photons cannot escape. Thus, the data is not lost, only moved up. This duality theory does a good job of explaining these and other modern mysteries of the universe, but it has several problems. For example, the Ads-CFT correspondence works in a negative spatial constant universe model. However, according to current observations, our universe has a positive constant value and is still expanding. So, we probably don't live in a finite universe. For example, in 1929, astronomer Edwin Hubble concluded that the universe was continuing to expand and that this process could continue forever. Therefore, since our observations are limited, the question of the infinity of the universe remains open. This point is crucial to the whole theory. So now the idea of Ads-CFT has mathematical value. But if we can find answers to all the findings of the theory, we can prove that the universe is a hologram. The question of what our universe is worries not only physicists, but also philosophers. In 2003, philosopher Nick Bostrom suggested that some scientists, such as Elon Musk, think it's somewhat possible. What if we are living in a simulation? In his paper, Bostrom argues that one claim about simulation capability must be true. First, humans will die before they reach a technological level that would allow them to create the most complex simulations. Second, it is highly unlikely that an advanced civilization would be interested in imitating its history. 3 advanced civilizations are creating simulations, and we live in one of them. So, if the third idea is true, we could live in a completely simulated world like computer games. Of course, This hypothesis cannot be tested empirically, but we may have some evidence to support the simulation hypothesis. About the speed of light. According to Einstein's theory, we know very well that the speed of light is limited to 186,000 miles per hour. Therefore, all the light we see from the stars takes a long time to reach us. A simulated device cannot have unlimited computing power. There must be some limits, and it's these limiting artifacts that we can observe at the limit of the speed of light. So, if this hypothetical computer processor running the simulation could perform one operation per second, it will have a warranty of 186,000 miles. In particular, the simulation can also explain the principles of quantum mechanics. As with subatomic particles, we define their state by looking at them. Thus, based on the simulation hypothesis, we see only the indicated part of the universe graph, and the rest of the graphs remain empty. And yet, despite the interesting explanation, by limiting the speed of light, a simulated universe is considered a speculative hypothesis because it cannot be proven or disproved. Maybe someday, if this hypothetical computer matrix starts to fail, we'll reconsider this idea. So, the universe is still a great mystery to us. We cannot believe that everything we see is not an illusion. As we have said, we are aliens to the universe, but what if we should never live? The Earth, the Sun, and our galaxy were never meant to be. CERN scientists believe that symmetric matter and antimatter must have been created after the Big Bang. So, if this scenario were to happen, all the particles had to come together to destroy the whole. However, something has created an imbalance between the two substances, and it is not yet known what it is. So we can say we are happy because we are here now, and we would be able to observe the universe and discover all its secrets. Do you think that one of the most fundamental aspects of our lives is nothing more than a complex illusion? Time, the force that governs our existence and seems to dictate the rhythm of our lives, is not what it seems. For example, time seems to slow down for objects traveling near the speed of light, and it flows at different speeds depending on the force and gravity around us. Have you ever considered that time may be a figment of our imagination, a construct our brains come up with to make sense of the world? In search of the truth behind this mysterious concept, you will have to step into the unknown and question everything you know about time. Time, in its simplest form, is a tool we use to measure change and organize the complex events that make up our lives. Our ancestors needed a way to keep track of natural cycles, like day and night, or the changing of the seasons. It was important in coordinating activities such as farming, navigation, and religious rituals. Early methods of telling time were based on natural phenomena, such as sunrise and sunset, the phases of the moon, and the positions of the stars. As human society has become more complex, so have our ways of measuring time. To divide the day into smaller and more manageable parts, we developed instruments such as sundials, water clocks, and finally, mechanical clocks. Calendars are designed to track the passage of long periods of time, such as months and years. Different cultures have developed their own unique calendars and timekeeping systems, reflecting the diversity of people's understanding and interpretation of time. Although timekeeping systems help us manage our daily activities and long-term planning, the perception of time remains a deeply personal and subjective experience. Our brain processes and interprets time differently, depending on factors such as age, emotional state, and cultural background. This suggests that time is not a fixed universal phenomenon, but a flexible construct shaped by our experiences and needs. Despite the presence of time in our lives, it remains a somewhat illusory concept. This begs the question, is time an objective reality, or is it a construct created to bring order to our chaos? So, let's look a little deeper into the history. The traditional understanding of time as an independent, constant entity was challenged by Albert Einstein's groundbreaking work in the early 20th century. Einstein's theory of relativity introduced the concept of time as a measurement, forever changing the way we think about this mysterious phenomenon. Einstein's theory of relativity arose from the nature of light and the concept of absolute space and time that was central to classical physics. He argued that the laws of physics must be the same for all observers, regardless of their relative motion. This revolutionary idea led to the development of two related theories: special relativity and general relativity. In his theory of special relativity, Einstein showed that space and time are not separate entities, but are bound together in a single continent called space-time. In this four-dimensional frame, time is transformed into a fourth dimension, and events are represented as points in space-time. This concept overturned the traditional view of time as an independent variable, showing that it is an integral part of the structure of the universe. Einstein's theories also showed that time is relative and depends on the reference of the observer. According to the theory of special relativity, two events that appear to one observer at the same time may appear to move relative to the first to a second observer at different times. This phenomenon, also known as relative relativity, makes it difficult for us to perceive time as an absolute and constant unit. General relativity extended the ideas of special relativity and brought gravity into the picture. According to this theory, large objects such as planets and stars cause periodic distortions, and this vein is captured by the force of motion in it. The presence of a large object can also affect the passage of time, resulting in a phenomenon known as gravitational time dilation. According to the theory of special relativity, time dilation occurs when two objects are moving at relatively high speeds relative to each other. If an object is moving faster, time passes more slowly compared to a stationary observer. This effect becomes apparent when approaching the speed of light. This phenomenon is best illustrated by the famous twin paradox. In this case, one twin travels close to the speed of light, while the other twin remains on Earth. Upon return, the traveling twin will be younger than the earthly twin due to the time difference. In general relativity, time dilation is also caused by gravity. Time moves more slowly in stronger gravitational fields, such as near large celestial bodies such as planets or stars. This effect was tested experimentally using atomic clocks located at different altitudes. Clocks closer to the Earth's surface run slower than clocks at higher altitudes where gravity is stronger and gravity is weaker. Time dilation, although seemingly illogical, has been experimentally verified and has practical applications. The best example is the Global Positioning System, or GPS. Earth-orbiting GPS satellites experience time dilation due to acceleration and gravity, which must maintain accurate time and location. Furthermore, gas pedal experiments for high-velocity particles have confirmed that particles traveling at the speed of light experience significant time dilation, as predicted by the theory of special relativity. Before Einstein's theory of relativity, time was considered the unchanging and universal background for all events in the universe. Isaac Newton, for example, believed in the concept of absolute time, which is uniform and flows independently of the events it measures. However, discoveries related to time expansion. The theories of special and general relativity refute this notion with the relative nature of time, and prove that time is not a constant but a variable quantity depending on the motion of the observer and the surrounding gravitational field. The traditional view of time as an absolute entity also implies a strict adherence to casuistry, where cause always precedes effect. However, the relative nature of time in relativity theory suggests that the order of events can depend on the reference of the observer, which can lead to cases where cause and effect appear to be reversed or simultaneous. This complicates our intuitive understanding of randomness and forces us to rethink our ideas about the way things work in the universe. The concept of the arrow of time, the idea that time flows in one direction, from the past to the future, based on our understanding of the world, has also been questioned. However, relativity's relativistic nature of time and random reversals force us to reconsider whether the arrow of time is a fundamental aspect of the universe or a construct of human perception. As the traditional view of time as an absolute entity was undermined by the discoveries of relativity theory, some scientists and philosophers suggested that time might be an emergent property rather than a fundamental aspect of the universe. From this point of view, time arises from the connection and interaction between objects and events, rather than being independent of them. Leaving aside the problems of Einstein's theory of relativity, we move into the more confusing world of quantum mechanics. In this realm, the nature of time becomes confusing and ambiguous, as the rules governing the quantum world defy our everyday understanding. Quantum mechanics is a branch of physics that studies the behavior of particles at the atomic and subatomic level. It is governed by a set of probability rules that differ from those of classical physics. In the quantum world, particles can exist in multiple states at once, a phenomenon known as superposition, and their properties can only be determined by measurement or observation. The concept of time in quantum mechanics is very different from the concept of time in classical physics. While classical physics describes time as a continuous and absolute unit, quantum mechanics treats it as a discrete numerical parameter. This time leads to situations that lose their traditional meaning and play an abstract role. For example, consider the following everyday scenario. You watch wild animals and see how they behave differently when they know they are being watched. As you get closer to them, their behavior changes, and it becomes difficult to understand their natural state. This example illustrates the observer effect in quantum mechanics, also known as Heisenberg's uncertainty principle. In the context of quantum mechanics, the observer effect refers to the idea that active measurements or observations can perturb the state of a quantum object, such as an electron. Just as your attempt to observe wild animals affects their behavior, observing or measuring a quantum object can affect its position or momentum. Heisenberg's uncertainty principle states that the position and velocity of a quantum object can be known simultaneously with absolute precision. The more accurately we measure one property, the more accurately we can know the other. In the quantum world, the act of observation or measurement can collapse the wave function of a particle and move it from a superposition of multiple states to a specific state. This process is inherently problematic, and the outcome cannot be predicted with certainty. Considering the phenomena of quantum superposition and the observer effect, it becomes clear that our traditional understanding of time as a linear progression may not be correct at the quantum level. Instead, the quantum world offers a more fluid, interconnected vision, where the boundaries between past, present, and future are not as rigid as we think. As we have seen, our understanding of time is closely related to our understanding of space. This complex relationship has given rise to many theories that attempt to explain the nature of space.